Now let's talk a lot more about the equilibrium state. And the first thing I want to say about it is that in principle, all reactions are reversible. And that means that the reaction can go in the forward direction or in the reverse direction. So let's pretend forward is that way and reverse is that way. Um, and in fact, they can go forward and then back, as we'll see. But to show this, we are going to use a double arrow, and that's called an equilibrium arrow. And you can draw it many ways. So typically when I draw it as two single-headed or single-sided arrows. Sometimes Microsoft Word and some of the programs I draw will draw it like this. Sometimes you'll also see it like that. Anything that indicates with the arrow on both sides is going to indicate that the reaction go from reactants to products, and that the reaction can also go from products back to reactants. And since we are chemists, we are nothing if not control freaks, and we want to make the reaction go whichever direction we want by manipulating the reaction conditions. And so we have to define the things on the left as the reactants now. That will always be the reactants regardless of which direction the reaction goes, and the products are on the right. So, and just remember from our previous work, many reactions appear to go one way from reactants to products, but that was only because in our beginning studies of chemistry, we chose those reactions. And all reactions can go either way. And part of what we're going to figure out is which reactions can go which direction under which conditions. Now, here's an example of a reaction that we've studied before, in which we said if you had lead ions and chloride ions, it produced lead 2 chloride, and that was because lead 2 chloride was insoluble. Of course, as we peel back the layers of the chemistry onion, we find that things are a little bit more complicated, and what I'd like to do is I'd like to show a video to demonstrate this part.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
Let's see if I can get back to my video here. There we go. So that was an example of the effects of temperature and the ability of heating a solution makes the reaction go backwards. And instead of saying backwards, it makes the solution go, the reaction go from products towards reactants. From products towards reactants. And as we'll see, when you go from products towards reactants, we will call that shifting a reaction to the left. Or oftentimes just shift left. Yeah. There we go. So reactions that we previously only looked at as going towards products, we can now make them go from products towards reactants. Now let's talk a little bit more about what the equilibrium state is. Chemical equilibrium is the state at which the concentrations of reactants and products do not change with time, and yet the forward and reverse reactions are still going at equal rates. And so we have two examples here. One is the vapor pressure of water. We've talked about the vapor pressure of water before, and as an example, if you have an Erlenmeyer flask with a rubber stopper in it, and you have a solution of H2O liquid in the bottom, what will happen, what is constantly happening, but what will happen is that the H2O will evaporate to become H2O gas, and initially more will evaporate than will condense. At some point, though, you will set up an equilibrium between these two, the liquid and the gas states or phases of H2O. And when that is true, that's what we call that the partial pressure, so let's say at equilibrium, the partial pressure of H2O gas equals the vapor pressure. If we remove the rubber stopper, some of the H2 gas will escape and the H2O liquid will keep evaporating. It is only in a closed container that we will get to equilibrium. Otherwise, the H2O gas will escape out into the atmosphere. Now, dissolving of sodium chloride takes sodium chloride solid and turns it into sodium chloride that is dissolved or aqueous, and because it is a strong electrolyte, it dissolves and breaks up into ions. Now if we had H2O liquid and we had a pile of sodium chloride solid, so the sodium chloride solid would dissolve into sodium and chloride minus ions, and then eventually at some point when you got enough of the sodium and chlorides, and this time equilibrium is established, so at equilibrium you are at what's called the solubility limit. And the approximate solubility limit of sodium chloride is at 6.7 molar. Sodium chloride. Previously, we had considered that sodium chloride was just soluble, but there is a solubility limit. And so you can actually get to equilibrium, and then you can actually, and at equilibrium, the sodium and the chlorides forming the ions and forming the solid are happening at the same rates. Now, reactions are always going towards the equilibrium because at equilibrium, the reaction is at its lowest energy state. And we will talk a lot about what that means, especially when we talk about thermodynamics. But for now, I want you to know this is true, that just in the same way that this pen falls to the ground because it is going to a lower energy state, reactions are going to their lowest energy state by getting to equilibrium, okay? And again, I don't expect that to make sense right now, but it is true. And we'll talk about what it means.